Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz. I'd just like to say thank you so much for joining us today as we look at different ways that we can help you with your application and being able to look at the topic today in regards to torque limiting technologies. And so let's go ahead and get started. If you do have any questions that you'd like to ask, we will be doing a review segment at the end of the presentation. Feel free to go ahead and type those questions into the chat, and we'll go ahead and review those after the fact. So with that, let's go ahead and get started. So when we first look at a lot of the different items that we generally talk about, we always seem to start out with what are the fastening risks that are involved in not having a good torque control process. And so in that case, for today's discussion will also be the same. We will begin with some of the things that allow us to be able to look at and see what areas that we can go ahead and try to improve on, and what are some of those risks that are associated with that. And so the first one is going to be over torquing. And so we want to make sure that we're getting the correct clamp load on our fasteners, and anytime there is any type of over torque, we have a danger of stressing the fastener to its yield point and then failure. And so if there's any type of vibration that may happen or shock, that could certainly push that fastener, if it is in that yield point area, to simply fail. So over torque is one of the big risks that we face. On the opposite end of that, obviously, is going to be under torquing. So if there is a fastener that does not have the correct tension or clamp load on it, and it's under torqued, again, any type of vibration or shock, we can have that fastener loosen even more, and then we have failure of the parts separating. Next is going to be material breakage. If we do have a failure with a particular part, that may then increase other parts within that assembly to break. And so then we're looking at different types of scrap or different items that will need to be reworked, but could present downtime for the assembly process. And then we also look at any type of safety critical applications where the torque is really important, that if a fastening failure does happen, that could certainly result in some type of bodily injury or worse. And then finally, human errors. The part of the factor that often and sometimes gets overlooked is the operator and their contribution to the fastening process, and how can we go ahead and help to remove any type of possible errors that may be presented by the operator in the application with the lack of any type of error proofing process within that specific aspect of the fastening process. And so again, this all leads to torque control and how we can make sure that we're getting the best clamp load that we can for that particular fastener. And that is all done with torque control. And so the items that we'll be discussing today are going to be around torque limiting technology within the hand tool category of the fastening process. And so a lot of hand tools will have a torque signal or other information that will allow the operator to know that they have reached their specific torque value. But we'll be looking at specific ways that we can help to eliminate any type of operator influence that may happen within the fastening process. And so what's going to be the best use of technology within the torque limiting application for your particular app or your particular scenario or application? We're going to be able to helpfully answer that question today. So let's go ahead and look at some of the different factors that go into being able to select a hand tool for your particular application. And it's going to be based on the requirements, obviously, of that application. What is going to be the error or acceptable out of tolerance, or what type of repeatability do you need for a specific application. You look at the fastener type that may be needed for your application, what type of safety or quality standards go into that, as well as you're going to be looking at using a preset hand tool or an adjustable hand tool, and the ergonomics as well that go along with that. Do you need a torque screwdriver, or will we be looking at a torque wrench, or a combination between one or the other based off of how the part is positioned for the operator? And so all of these things combine together into what tool is going to work best for your particular application. And so when we look at hand tools in general for different types of torquing applications, there are two kinds. We have a preset and we have an adjustable hand tool. And so the difference between those two may seem obvious. The preset hand tool is one that does not have a graduated scale on the outside. You can't look at it and know where it is set. All of the internals for the torque value are done, the internal adjustments are done inside of the tool. That tool is then validated on a torque analyzer to make sure that the torque that we are getting is what the tool is producing. You're also going to see enhanced production reliability with a preset tool. That tool is set at one value and it's going to be repeated for that particular application with the same torque value every single time. And then when we look at adjustable tools, obviously, again, they're going to be adjustable with a graduated or a digital scale that maybe have the opportunity for the operator to externally manually adjust those tools to a specific torque value. And these obviously can be good for switching between different torque values that may be needed for a specific application or series of steps within a certain cell build or part of the assembly process. So these tools also work great as far as field service kits or as an OEM kit that is included with any type of service or maintenance that may be needed as well, to give the operator or the technician the ability to have different torque values to be able to use. So when we look at torque screwdrivers, some of the quality standards that go along with the use of those is going to be the ISO 6789. As it relates to torque screwdrivers, those have a value of plus or minus 6% of the indicated setting for the repeatability of those tools for it to be able to qualify as an ISO 6789 tool. In that regulation as well, the tool must remain within its calibration range for at least 5,000 cycles based off of that particular standard. And so those are dealing with torque screwdrivers only. There is some change, and when we look at the torque screwdriver, or excuse me, the torque wrenches, and we'll note those at that time as well. And so what this all comes down to is when we're looking at the torque screwdrivers and the different types of torque limiting mechanisms that are available. You have the clutch mechanisms, and how do those clutch mechanisms affect the accuracy and consistency of a specific type of tool. And so not all torque screwdrivers are created equal. And so let's take a look at some of the differences between different styles or manufacturers of the clutch mechanisms, which also relate to the cam. Now, well, not all, but most screwdrivers and torque wrenches for torquing processes all use a spring and the spring constant rate of compression for the ability to generate a specific torque value. So as we compress the spring in our turning or twisting force, this allows us to be able to accurately deliver a specific torque. Now, how that spring gets compressed and then how it gets decompressed is different across different types of screwdrivers and different types of manufacturers. And so if we take a look at an example of some other tools that are available, we see that in the first example, the cam mechanism here, and let me just do one thing that will make it a little bit easier. So if we look at the cam mechanism here for this particular tool, we have our spring, and as this spring gets compressed, we have this series of 3 ball bearings that are in this little sleeve, and this is sandwiched in between this mechanism here. And so as the twisting force happens, once the spring gets compressed to a certain value, those ball bearings will then move into a different lobe here or indentation on that particular set of mechanisms. And that's how these particular or this particular style of tool works. So we have the ball bearings that are pushing up onto the spring, and as that spring gets compressed, it gets compressed to a certain point, and then the ball bearings will then move into the next position. In our next example, we have this particular driver where it has the spring mechanism inside the housing, and then we have stationary ball bearings inside of here, and then as the drive turns, these ball bearings will then allow this mechanism to move, and it will then compress the ball bearings and the spring, and then release after it goes up and over the particular segments here on the drive mechanism. This is almost identical to the first, except for there is just not as many particular indentations on the mechanism up here. And then finally, we have the same type of mechanism as this one, except for this is a little bit different, where it's at the back end of the tool, and again the ball bearings will remain in their lobe, and the arm will come and push those ball bearings down, compressing the spring and allowing the torque to be achieved. And so these are all different ways that the torque is generated by the compression of the spring inside of the tool body. And so when we take a look at the Mountz mechanism, it uses a different type of clutch than what would be with all of these styles. It's more of a ball bearing, a ball clutch type of application, and we use a radial cam mechanism in our torque drivers. So if we take a look at the inside of the tool, you can see we've got three different cams. Excuse me, we have three different ball bearings inside of a 6-lobe cam. And so as the tool is being twisted and torqued, the cam is pushing in on the 3 ball bearings, which go into the main housing. That main housing contains a larger ball bearing that also has a thrust washer on it, and that then is compressing the spring. So this gives us a really nice and smooth operation as far as the torquing is concerned. And so I'll just let the animation play here, and you can see that as the tool is torqued, we get that compression of the ball bearings. And then so this position here shows that when the driver is turned, those ball bearings again push onto the main ball bearing, and that will compress our spring. So the cam lobe itself and that design again pushes in on the 3 ball bearings that then will push on the larger ball bearing. So it gives us a nice smooth operation within the torquing process. And so with that also gives us the ability to add a couple different styles to that particular configuration of tool. We can have a one-way clutch, meaning that the tool will only torque in one direction, and then the other direction will be a static. This would be good for any type of repair work where you may need a positive value or a positive setting on the tool itself to remove a fastener, and then go ahead and torque that in the fastening direction. We also have a impact-free clutch mechanism where the design of the cam is has a much smaller slope and reduces the number of cams. So if there is a really delicate type of material that needs to be torqued, such as a ceramic or a really delicate type of application, we can do that with an impact-free type of driver. And so let's go ahead and we can go ahead and look at the screwdriver in action. And so I have one of our FG drivers here. And again, as the cam mechanism, which is right here, compresses, it will then go ahead and push up and compress our spring to give us our torque that we need. So we have our torque analyzer. This is our Easy Torque 3. And for this, we can go ahead and see where we're at as far as our torque that we're being delivered. We do have our ability here to enter in what our tolerance is. And again, we're at plus or minus 6%. So anything below the green zone is going to be under torque. Anything over that is going to be over. We also have the ability to add statistics and do some other things in monitoring the serial number, but I can simply just go ahead and cam the tool and it's going to give us what our value is. And so in this case, we have a target which is much higher than what we're seeing here on the screen. So if I clear this, we can come back and we can take some readings. All right, and we need to set this tool to be at, say, 125 Newton centimeters. So we have an end cap that goes on the back of the tool here. Down below, there is a torque mechanism down here that we would loosen the locking mechanism. And then we can come into the back of the tool with the adjustment key and come in, and we can go ahead and turn in the clockwise. That's going to go ahead and increase our torque value. And let's go ahead and change our value on the analyzer. So we can set our target here at 125 and then come back to our operation mode and we can see where we're at. So it's a little bit higher than what we need. So again, we can come back in and make our adjustment. Let's back that off just a little bit. All right, so I think we're pretty good at this value, but this demonstrates how the tool helps to prevent any type of additional torque because again, the tool itself is camming within our radial cam design and you can't add any additional torque to that. So in this case, we can just go ahead and we can tighten up our locking mechanism that we have in the back down below, and then we can go ahead and then attach the end cap. And if this is going to go out onto the floor, we could put a calibration sticker or whatever notification that you'd like for that on that particular tool. And so that is the use of the FG torque screwdriver. So when we look at torque wrenches, there are a number of torque wrenches that are available that can be used. We have dial wrenches, there are beam wrenches, there's electronic wrenches, there's cam over style wrenches, we have click wrenches, and then also some breakover style wrenches as well. And so what all of these wrenches have in common is that they signal the operator once a specific torque value has been achieved. And so that's kind of important, obviously, when we're trying to make sure that we are delivering the proper torque in our assembly process. And so when I talked about the different standards for torque wrenches, we have two separate accuracy standards. So any value that is below 10 Newton meters is going to be plus or minus 6%. Any value over 10 Newton meters does tighten up to be plus or minus 4% of the indicated setting. And so the calibration requirement is the same at 5,000 cycles. Now, at Mountz, our calibration for our FGs and our FGCs are twice and 4 times that amount that we guarantee. So just a little note for you there as well. And so when we look at the torque wrenches, and as I mentioned, the torque wrenches will all signal when the torque is achieved. However, that does not guarantee the amount of torque that is being delivered for that particular application. And so the most widely used and most affordable, most readily available type of wrench is going to be the click wrench. And so the click wrench itself, if we have here, basically inside of the cylinder tube, we have a fulcrum point where the end of the head meets the portion that is controlling the spring. And so when we get a certain amount of flex or torsion on that, we hear a little click, and that is the what is called the pivot block hitting the inside of the tube of the wrench. Now there are a couple other styles of wrenches that act similar. So a split beam style wrench would have a similar type of click or notification that torque has been achieved. But what it does is it signals that the torque has been achieved, but we also have the ability to add additional torque to the application very, very easily, because once that wrench clicks, we have about 3 degrees of movement before we are adding additional torque to the application. And that's basically just because as the wrench is being pulled, once we hear the click, if that operator does not stop pulling it, or you may see operators that will double click sometimes triple click, you are adding a tremendous amount of additional torque to the fastener, and that may not even be something that the operator is aware of. So if we look at this on a graph, you can see we've hit our torque value, the wrench clicks, but if we keep pulling on that, we are adding additional torque to the assembly. And so while the click wrench is a good wrench that can be used in a lot of applications, if you have a critical type of application, or you are seeing inconsistencies from operator to operator in the use of a click wrench, that may be the issue. And so this kind of ties back into the human aspect of what we normally would consider their involvement into the consistency of torque that's being applied. So right now we'll go ahead and take our poll for today. Now our poll question is what in your experience when using click wrenches or for your fastening applications, one, does the wrench normally meet your application? Are you experiencing some over torque issues? Are you experiencing frequent over torque issues, or are you not aware that the operator influence and over torque risks of a click wrench, or you currently do not use any click wrenches? And so we'll go ahead and give you just a few minutes here to go ahead and take a look at those. All right. Thanks very much for participating in the poll. It looks like everyone that is using the click wrench, that it seems to be doing the job for them in their application. So it's always good to know that when you're using the click wrench, on how operator dependent it is. And so if you are seeing any type of issues, that may be where you'd want to look. And so some of the other styles of wrenches that we work with and deal with that can help alleviate some of those problems. The first one is going to be a breakover style wrench. And so this wrench basically does what the name implies. Once the wrench meets its particular torque value, the head mechanism will begin to break, and so or break over. And that can be a maximum of 90-degree break. Could be set with a collar to 20 degrees. So basically, as the operator is using that tool, once the wrench begins to break, you know that they've hit their torque value, and you've got a much greater window to stop pulling on the wrench. So there is no over torque within that particular application. And so what that looks like basically on our graph is we go up to our torque value, the wrench breaks, and now we have a greater distance to stop pulling to make sure that we do not add any additional over torque to that particular application. Next is going to be the cam over style tool or the cam over wrench. And this is very similar to the screwdriver example that we looked at. This particular tool will allow the operator to actually go ahead and pull on the wrench. Once the wrench cams over, the torque value has been achieved, and the operator can come back and pull on that specific fastener or do it as many times as they would like, and the wrench is not going to add any additional over torque to that assembly process. And so these wrenches are very good for really safety critical type of applications, or any type of R&D, or excuse me, any type of auditing applications where you can come at the particular fastener that you may be using, have the wrench set at a certain torque value, and go ahead and run that on the fastener. You're not going to be adding any additional over torque, but you could see if the fastener was under torqued, if there was any movement in that fastener at all. So the cam over wrench, again, is going to allow the operator to apply torque, and it will never allow them to add any additional torque to the application. And so if we looked at this on the graph, we could come up, we would reach our torque value, the cam was reset, we could run it back up again, the cam will then again reset, and we can do that as many times as we'd like, but we can never do or apply more torque than what is going to allow us for that cam mechanism. And so if we looked at that particular operation within the animation here, you can see that very similar to the torque screwdriver, as the cam is turned or the drive is turned, it's going to push in on the follower, compress the spring to a certain point, and then the cam will reset. So we can never add any more torque than what is necessary for that particular application. And so if we were looking at these tools as what would be considered a good, better, or best scenario, for final torque accuracy, the cam over wrench would be the best option for us, followed by the breakover wrench. For an error proofing type of process, again, the cam over wrench is going to be best for that particular type of operation. However, if you have a specific target of torque or a specific price point that you need to meet, the click wrench again will satisfy those needs at that point. And so with that, let's go ahead and we can look at how we can see what the results would be of that particular type of assembly. And so if we take a look at the cam over tool, and so I can go ahead and I can put this on our torque analyzer and take a reading, and we can see where we're at. So we're probably going to, we'll need to adjust the target here, and we can change this to 300. And now, there we go. So even if I keep going here, we're not adding any additional torque to that process. So we can never add any more than that with the type of cam. And if we did need to make any adjustments to this tool, we could do the same as we did with the screwdriver. We remove the end cap here, go ahead and come in with our adjustment tool, make our adjustments, and then we can go ahead and retest it on the analyzer as well. And so again, as this wrench cams, we're not adding any additional torque to that process. If we look at the click wrench, and so we'll see where this one is set. So we're a little bit lower. So if I change the mode, this is going to give us the ability to see at which point the wrench is going to click. And then we can also see at the value at where the wrench ends up. And so if I pull on this very, very slowly, you can see that the wrench is camming at about 120. So let's go ahead and change our torque target. Come back here to our operation. And so with that pull, you can see it did click at the right point at 121, but we had a tremendous amount of over torque with 233. So if I pull on the wrench go. You can see that if you get the correct feel for it, you're going to be seeing the ability of the where the wrench is clicking, and then any additional over torque with that tool. And so that the final torque value is going to vary greatly on how the operator is pulling on that wrench, how they're feeling that day. Did their favorite team win or lose? Are they taking it out on the application? There are a tremendous amount of factors that go into the operator using the click wrench. This type of test can be done on any of our torque analyzers. It could even be done on your application with the use of a rotary type sensor. So if you did want to see how your operators are using their particular tools, you could verify to make sure that you're getting the correct amount of torque that you would need. Now, finally, we'll go ahead and look at our breakover style wrench. And so this, again, as we go ahead and torque on this, this particular joint right here is going to break over. And once that does, then we've hit our torque value. So let's see where we're at here with this one. So let me change the mode back to peak. So let me just move this up just a little bit so we can see the mechanism. So as this begins to break, you can see that the elbow here has met, and we're not adding any additional over torque until we were to actually go past this, and we could turn the wrench the full 90 degrees for that particular. But that's how the breakover wrench can work. And so these tools have the ability to have multiple styles of heads. So if you did want to use them interchangeably, that is possible by adding a ratchet head here. We could also add a open end head, or a ratcheting head like this, or even a boxed end head. Again, for doing any type of tightening. If you did need to get into some very tricky areas with an Allen hex key, you could put an Allen head key on here as well, and be able to hit a very restricted area that you may need for any type of operation like that. So the breakover wrench is a good option that way. And so with that, that's going to kind of lead us to the end of our presentation. But this just demonstrates the different types of torque limiting technology that we have, that we can use, and that gives you the ability to choose what's going to be best for your particular application. So with that, we'll go to any questions what we have. And Chris, do we have any questions?
Hey, Dave, thanks. Yeah, I got a couple of questions. The first one was on the Hicks, those head keys you were showing. Do you offer custom size heads for that wrench?
On the breakover tool, yes, there are custom heads that are available that we could make for you. One of the things that we have done quite a bit of for some customers is being able to provide them with custom Allen keys that have a number of different bends in them. As I mentioned, trying to get into a specific spot that may be a little bit difficult, but all of those can be made with a custom hex head for sure.
All right, thanks, Dave. Next question was, how often does the wrench or screwdriver need to be recalibrated?
So the ISO specification that we looked at, ISO 6789, says that it must maintain at least 5,000 cycles, and that whatever that particular value may work out for a specific application, you could track it that way. There are some customers that will come in and they were going to test or validate their tool to make sure that it's within its spec. They'll do that on a monthly basis, maybe a weekly basis. We have some customers that do the verification right before the tool is used. There are in special circumstances where that particular tool is tested a number of times, that those results are documented, the tool is used, then the tool gets returned with another set of readings, and then the tool is put away. So being able to validate and calibrate the tools are typically done on a cycle-based or a time-based, but they can also be done on a verification. If the tool is still performing within the tolerance, then that tool could be used. If it is being tested on a torque analyzer that has its current traceability certificate of calibration, then that tool then is now traceable to that standard for that analyzer, and it would be considered within its specification, and then again would be traceable to the cert on the analyzer, and which is traceable to the transducer that analyzer is tested to, and all the way to the dead weight. So I hope that answers it.
Oh, yeah. Thanks, Dave. And then lastly, a follow-up question on the preset tool is, once it's set to a torque value, can it be adjusted to another torque value for a future project?
Yes. Each preset tool has a certain range that it can work from. So, for example, if it's, say, 1 to 10 Newton meters, that tool can be set and used anywhere within that range to be set. It can go ahead and be in use. It then can be recertified at a certain value, tested on an analyzer, and now it could be used for that torque value as well. So it's not just simply one torque value. However, if you do want to change it, it just needs to be verified and validated on a torque analyzer.
All right, Dave, thanks. It looks like that's all the questions we've got today.
All right. I want to thank you so much for joining us today, and we look forward to seeing you in our next webinar next month. Thanks so much. Have a good day.